So this article is really interesting, although it uses a relatively different paradigm for reasoning. So we generate common sense explanations. For example, we assume that your sentence is wrong, some sentence, and you say why. For example, you give an explanation that why, using common sense, it is not according to the common sense. But we should discover some bridge concepts in the knowledge graph, such as concept net, to prove and make an explanation. So this is an article in 2020, and I want to explain this one. So the statement, the school was open for summer, you can say this is wrong. This could be wrong because your explanation could say that summertime is typically vacation time, and vacation time, at vacation time every school is closed. So this contradicts this one. So this argument attacks this one in the language of argument mining. So we generate explanations. So the idea is that we propose a method that first extracts the underlying concepts which are served as bridges in the reasoning chain, and they integrate these concepts to generate the final explanation. To facilitate the reasoning process, we utilize external common sense knowledge to build the connection between a statement and the bridge concepts by extracting and pruning multi-hop path to build a subgraph. We design a bridge concept extraction model that first scores the triples, routes the path in the subgraph, and further selects bridge concepts. So each of them has a loss. So this is the overall loss. Generation of that should be correct. You should find those bridge concepts like here, and also those node edge, node relation node, that triple should have a low loss as well. So we focus on the challenging explanation generation task, where the goal is to generate a sentence to explain the reasons why the input statement is against common sense. But if you just use sequence-to-sequence model, they have many semantic problems. And in general, for example, look at transformer. Transformer is very good for capturing the syntactic information. It captured a little semantic information, but not everything. That's why we have hallucination. And also you should know that those sentences should be factual. But many times we see that they are not factual. So those paradigms, simple paradigms, have many problems. So most existing language generation models do not generate explanations that are faithful to common sense, because they ignore the semantics. So they should integrate abstract meaning representation, AMR formalism, for example, to have a better understanding of which part is semantically related to what question. So thus explicitly incorporating external knowledge source is necessary for this task. Since the nature of explanation generation task involves using underlying common sense knowledge to explain. Locating useful common sense knowledge from large-scale knowledge graph is not trivial in general it requires multi-hop reasoning. So your task could be seen like this. You have a sequence to sequence of X to sequence of Y. But we decompose that to, we have a bridge concept, Y condition on this bridge concept, and bridge concept condition on your source sentence. So bridge concept, I can say that, is a type of target concept which is not inside the source concept. And this is the statistic, the proportion for different hops. So we use fused concept representation. First we have 100 presentation, and then you use by attention is a kind of attention networks that uses not only your tokens but also your representation that you have obtained. And finally, you represent your text by multi-layer perceptron of max pooling of this concatenation. And you can also use the concept distance. We want to reduce that distance as much as possible. So we describe the core component of our method, which extracts the bridge concepts for further explanation generation. So it first scores triples, that loss of triple, if you remember my first slide, on the subgraph to downweight the noisy path. Then it aggregates the path scores to each connected concepts by path routing process and deactivates the nodes with low routing scores. Finally, it selects top-ranked bridge concepts from the activated nodes. So this is triple scoring. We concatenate the head, relation, and the tail. We use max pooling and a non-linear combination of your sentence and your embedding that is here. And if your edge is inside the path, so it becomes 1, otherwise it becomes 0, so automatically captures just the edges along the path, and you want to maximize this probability. And for path routing, we describe the path routing process, which involves the propagating the scores along the path to each concept on the subgraph from the source concepts. So for each concept C, we consider all shortest paths that starts with the source concepts and ends with C monotonically. By monotonically, they mean that the concept distance of each node increases monotonically. So distance is like this, and then this, and then this, and the distance should always go up. And for concept selection, because there is another loss. We had 3 loss. If you remember, one of them is concept, with the other one was triple. And for concept, we use again this indicator function. So what is the probability of your bridge concept given your source? And you have explanation generation, because we want the final things to be readable, That's why you need that one. Sometimes they call it, I've seen it in different articles, they call it, if I'm not wrong, they call it back translation. So this is the inference problem. You have a source, you use the concept net, you find the bridge is important, and you give it to transformer to generate something meaningful. But you have very good features like this because you know the top ranked concepts, and this is the key. Otherwise, that transformer, that sequence to sequence model, we have done it several times, but the contribution is this part, that you have the bridge concepts. So as I said, we have triple, concept, and generation. By playing with these, you can see which one is more important for you. So it's like a multi-objective optimization, because depending on parameters lambda 1 and lambda 2, you have a set of Pareto optimal set, and you have common sense explanation data set. So it has 10,000 statements that are against common sense. So we assume that they are against the common sense, and that argument attacks the source argument. And we use recall, precision, F1 score, but for evaluation, we use these measures as well. And these are the results. This is the algorithm that I explained, and you can compare it. It's much better than just sequence to sequence model by 10%. And I've explained this for question answering. This bidirectional attention flow for machine comprehension.